So we're here today with a different style of video. We're doing it on paper. I got this pen right here. I got an assortment of pens right here because a few of them don't work. We got blue pens. I think this one's also a blue pen, black pen, red pen, and a green highlighter just to get some little colors going. So I have a problem here today from the quantum mechanics chapter, which I don't want to write down, so I'm going to just post it up on the screen here, a little screenshot. And I have it open in front of me over here on the computer screen. So it says a wave function for a quantum particle is given by psi of x equals ax between x equals 0 and x equals 1, comma, and psi of x equals 0 elsewhere. Okay, first I'm going to just write that down. Psi of x equals ax for x is between 1 and 0. This is how we write it down. This function applies for this region where x is between 0 and 1. 0 is less than x is less than 1. Elsewhere, wave function equals 0, else. Or another way you can write this is for x is less than 0 and x is greater than 1. So let's draw a graph here. We have the x-axis. Over here we're plotting our psi, which is a function of x. So at this stage I'm going to use some red, right? We got this region here between 0 and, let's say this is 1, let's say this is 2. So this region, the wave function is increasing until it gets to this stage, right? We don't know what the slope is. Actually, the slope is a, right? Because the function here is psi of x equals ax. This is the same as y equals mx plus b. Here, m is the slope, x is the independent variable, y is the dependent variable, or the wave function, and b is equal to 0. Nice. Everywhere outside of this, the wave function is 0, so it is literally a flat line. Right here, it falls off instantly, and it is a flat line. So this is what the wave function looks like. Let me actually just draw it in green so it's more visible. Boom, 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 boom. Let's read the rest of the problem. Very good to draw a picture. Rest of the problem says, find A, the value of the normalization constant A. Find A. We got 3 parts, B and C. B says find the probability of the particle. Find the probability that the particle will be between x equals 0.3 and x equals 0.4. Prob of particle being between x is equal to 0.3 and x is equal to 0.4. That's part B. C, the expectation value. Expectation value. All right, let's start off with part A. And in order to solve this, right, we basically want to find this here. How do we find that? How do we find the slope of this function? You have to use a condition that applies to the wave function. This condition is called the normalization condition. So I'm going to flip the page here. Actually, let me keep it clean for y'all. Keep everything like this. So the normalization condition is normalization condition. This applies to all wave functions, psi of x. And what it says is if you take the absolute value of the wave function, you square that, you integrate that over the entire space that you're working with. So in this case, it is space x, integration over x. All of this equals 1. So this is normalization, and sometimes you can see this as unity. Unity normally means 1. This is important. Basically, it says if I have some wave function here, right? Whatever the wave function does, maybe it's some crazy stuff like this. This is not our wave function. Our wave function looks like this. It drops off, it goes. It's a pretty simple one. Anyway, whatever your wave function is, if it's a function of x, you take the absolute value, you square that boy, and then you try to find the area over the entire bounds. And that has to equal 1. Why is that the case? Because this wave function is a probability density function. And probabilities normally are normalized to 1 meaning 100%. What this means is if I look all the way from infinity all the way to minus infinity over the entire space of existence, dx, I have a 100% chance of finding the particle over that space, right? Because the particle, we're saying the particle exists, so this is a way of kind of confirming that you can find the particle somewhere. If you integrate from another bound, let's say you start at bound A and go to bound B, you might have a number less than 1. Let's say you have 0.3, which if you multiply by 100, you get 30%. This means there's a 30% chance of finding the particle between this range here. Okay, so let's redraw our graph here. What the function looked like was boom, boom, boom. What this is saying mathematically, well, let's expand this over here. So if you haven't worked with integrals before, this is going to be a nice little introduction. I can basically break up these bounds into 3 different sections. There's one region where x over here is 0. All the way here, you go to x is equal to minus infinity. I'm going to break the integral up like this. So here I will do the normalization condition integral. I will put some brackets like this, and basically I will break apart the first integral from negative infinity to 0. Inside, I will put the wave function. I'm just going to keep it like kind of general like this. To that, I'm going to add another integral which starts at the end point that the previous integral ended at. Right? So we start from 0, then we go to 1. Why is this the case? Because the next point of interest is this x equals 1. So that's why I'm breaking up the integral like this. I will again put a little x here, dx. And I'm going to add to that another thing where I start with the end point of the previous integral here, and then I end off with infinity. So you could see this integral plus this integral plus this integral gives us this one. You start from negative infinity here. I'm just breaking it up. I'm saying integrate from negative infinity to 0, integrate from 0 to 1, integrate from 1 to infinity. Add all of those up. It's the same as integrating from negative infinity to positive infinity. Why is this the case? Because if you remember in our conditions in the problem, it said that the wave function is 0 anywhere out in this region here. So the wave function here is 0, the wave function here is 0. If you take a look at this, right here we're plugging in the wave function. We plug in the wave function here, we plug in the wave function here, we plug in the wave function here. In this region here, the wave function is 0. So 0 basically terminates this entire integral. This just goes to 0. Same thing here. Outside of 1 all the way to infinity, the wave function is 0. So we don't care about that. The area under this curve is 0. Same thing with the area under this curve. These are just zeros. The only thing we care about is this little region here, which is a non-zero area. So by the same kind of logic, this terminates, and we simplify our entire normalization condition to this singular integral over here, which I will write down like this: 0 to 1. Ooh, hold up though. Hold up. What we're putting in here is not actually psi of x. We need to put absolute value squared. I did this entire video and I forgot about this little square here and I got everything wrong. So make sure you have this. Take a look at the normalization condition in the summary. But basically what we have here, if we replace our wave function, right, we have ax, that is psi. So I'm just going to replace that. We have ax, absolute value brackets, square dx. This must equal 1. So now we have an equation here which we can work with, which will help us find a, because in this equation, the only unknown value is a. All right, let's keep working. I'm also going to move this sheet over here to the side. Actually put that right there. So what we have here, let me just rewrite it. An integral from 0 to 1 of absolute value ax squared dx equals 1. Let's simplify this a little bit more by distributing this square, right? This absolute value basically means if x or a inside is negative, just turn it positive. But since we have a square over here, it doesn't really matter. So we can just distribute the square onto the a, distribute the square onto the x, then we follow through with the dx, and we have 1. A is a constant by definition, so we can pull this out of the integral, but x is not a constant. It's actually the variable of integration, which you can see because there's a dx over here. This is the variable of integration. So if we pull out the a, we have an a squared over here. Integral stays the same from 0 to 1. We got an x squared over here. We have a dx over here. All of this equals 1. Now, if we want to find a, we need to determine what the value of this integral is. This equals some number. If we find that number, we divide it on this side, boom, we have an answer for a. So what is this integral? Let's solve it here on its own. 0, 1, x squared dx. What does this equal? This does not equal 1, right? Because this entire thing equals 1. I'm trying to find this integral on its own. So if you've taken some integral class, you can remember that there is an exponent rule. Normally you put square brackets like this. You put x plus 1 in the exponent, and then you divide by that exponent here. And then you carry the bounds here, 0 and 1. You see how there's a 0 here and there's a 1 here? I put the 0 and I put the 1 here. This is called the antiderivative. This is how you do an integral. Here, what we do is we put another bracket, and then we basically plug in this 1 wherever we see an x. So we put 1 cubed over 3, then we put a minus sign, and then we plug in this 0 wherever we see an x. So 0 cubed, then we put a 3 here. 0 divided by 3 equals 0. So this entire thing is equal to 1 cubed is 1 over 3. So this entire integral equals 1 over 3. Let's go back to our equation here. We got a squared is equal to 1 over this number, 1 over 3, which equals 3. We want to find a, so let's square root both sides. We get square root of 3, which I know is the answer because, like I said before, I did this whole problem. I forgot something and I saw that I got everything wrong. So then I searched up online what the answer was, and I can remember from memory it is square root of 3. So keep in mind what I just did here. Here are the steps. Start off by writing down what you know. Start off by drawing a picture. Write the questions. After that, we bring in the normalization condition. How do you know this is what you have to use? You got to do some homework. Now you know this is what you have to use because you've watched this video. Thank you for watching. Draw your graph, break up the integral. So you could break it up into 3 sections. The section over here, the section over here, the section over here. Wherever the wave function is 0, you can just remove that integral because the area underneath this and underneath this is 0. All you care about is the area under this. Technically, it's under this absolute value squared, right? Remember, we have absolute value squared. Do not forget that. If you just do this, which is what I did, if you just do this and you plug in a in here, you're going to get a equals 1. You can try this out for funsies. A equals 1 is incorrect. It's going to lead you down the wrong hole. And then you're going to get this incorrect. This is going to lead to B being incorrect and C being incorrect. So make sure you follow the proper normalization condition. If you're curious about what this is, search up online on ChatGPT, quantum mechanics normalization condition of the wave function. There's a lot of interesting stuff as to why the wave function is a probability density and why the normalization condition must hold. For now, I'm just showing you how to solve problems. So we're going to move on from here into part C. Let me actually save some paper here. Go like boom, boom. Sorry, I meant part B. Part B, we have to find probability. Remember how I said psi is a probability density function? Because it is a probability density function, if we plot it like this, remember how our function went like boom? Now we know that the a is square root 3, which is about like 1.7 something. I don't know. We know that the slope here is like about 1.7. Then it falls off here, and then it equals 0. So whatever this slope is, straight slope equals a equals square root 3. So we know some more information about the probability, about the wave function, sorry. Now, what I was saying before is, so here we have 1, here we have 0. Somewhere between is 0.5, and somewhere right before that is 0.4 and 0.3. So if I draw little dotted lines here, you can see this little section that I've cut out of the wave function. If we find the area under this curve, we will find the probability of the particle being found in this area, okay? I don't have too much time to explain all of that. That's just how you have to do it. Basically, what I'm going to say is probability densities are functions that if you find the area underneath the probability density, it returns probability. This is the same thing you learn in a probability class. It's the same thing that applies in quantum mechanics. So how do we find the area under this? We basically do an integral, between not infinity and negative infinity, but the ranges that you're looking for. So 0.4 and 0.3. In here, you put the wave function. This is why I was confused, because now we're integrating just the wave function. We're not integrating the wave function squared. So this is why I got confused in the previous time. If you know how to do integrals, you could do it this way, but I don't really want to do that. I mean, maybe I should do that actually. Let me see here. What we found before is that the wave function is equal to square root 3 times x. This is the function. It is literally a straight line. You can see it's a straight line right here because I've graphed it. So what can we learn about this? Let me pull out a new piece of paper. Redraw the graph. You see how many graphs I'm drawing? Don't worry about redrawing so many graphs. It is useful. We got boom, boom. So right here we have 0.3, and somewhere around here we have 0.4. If I determine what this is, this value here, this is psi of 0.3. And this value here, this is psi of 0.4. I plug this into a function. Let's just literally do that. So we have psi of x is equal to square root 3 times x. That means psi of 0.3 is equal to square root 3 times 0.3. Psi of 0.4 is equal to square root 3 times 0.4. Let me pull up my calculator here on Google. Calculator. So we got square root 3, close bracket, times 0.3 equals 0.5. I'll do 5.2. This is a number that continues on. So if you want to do an integral and get it exact and you don't want to round like this, then you have to solve the integral. But right now I'm going to show you a rudimentary way of doing it where you don't need calculus. It is the bootleg calculus, so to speak. This is how they introduce calculus. So first of all, let's calculate what this is as well. We got, let me clear this, square root 3, close bracket, times 0.4. Let's see what this bad boy is. 0.6928. Let's round it to 69. 0.69. So now we know that this is about 0.69 and this is about 0.52. Okay. So remember how we have to find the area under this shape right here, right? I want to redraw this shape right over here. Right? This is the slope over here. And we just found that this height over here is 0.52, right? This width over here is 0.3 to 0.4, so it's 0.1. We can break apart the shape like this into shape number 1, shape number 2, a triangle. And we also found that this height over here is 0.69. So that means the height of this guy, this little height of the triangle, will be 0.69 minus 0.52, which I will calculate here as well. 0.69 minus 0.52, 0.17. Nice. Now, if we find the area of this shape and we add it to the area of this shape, we will find the total area, which equals the probability. All right. If you don't want to do it with these addition of shapes, you can actually do an integral, right? Remember, if you had a crazy function like this and you had to find the area under here and under here, it's going to be really hard breaking this up into shapes that you could do, that you can use. This is why, God bless Newton. Newton figured out a way to do this really elegant way using integrals. But you guys can use integrals if you want. Right now, I just want to do it the old school bootleg way of adding shapes. So we got the area of this shape. Area of a triangle is base times height times 1/2. This equals the base, which is 0.1, times the height, which is 0.17, times 1/2, which is 0.5. This equals something. This is the triangle. Let's also do this at the same time. This equals base times height, which equals 0.1 is the base times the height, which is 0.69. So what we got is 0.1. My bad, let me erase all this. 0.1 times 0.17 times 0.5. Nice. Area of triangle 0.0085. Let's check 0.1 times 0.69 equals 0.069. Now we can add these two together to get total area. Total area. I'm going to add to this 0.00085. That looks good to me. Oh man, this does not look good. I don't think this is the right answer. 0.0775. I'm gonna actually check the right answer. All right, guys. I made a mistake. Again. I made the same damn mistake, bro. Probability is equal to integral between the bounds which we were looking for of the absolute value of the wave function squared. The same thing as the normalization condition. So I made a mistake. I guess we do have to use integral in this case. So this is part of doing the homework. You make a little mistake here. Actually, I don't even need to draw a picture because like once we square the wave function, we don't really need to like look at how it looks. So anywho, we have the wave function, which we found out was square root 3 times x. The wave function squared is equal to, distribute the square, we get 3 times x squared. Now what we want to do is find the integral between 0.3 and 0.4 of this. My bad, this is not a 3, this is a 2 here, dx. 3 is a constant, we can move that out to simplify the integral. 0.3, 0.4, we get a 3 here, we get an x squared here. Okay, I guess we do gotta use calculus here, guys. Sorry about my shape mistake there. And sorry about this. This is a lesson you guys can learn. Make sure you use the proper equation. Make sure you understand the difference between the wave function and the absolute value squared of the wave function. What is this difference? This is the mistake I made twice now. Anywho, now that I made this mistake twice, I'm not going to make it again, I promise y'all. Integral of this is the same thing that we saw before. So I have a 3. I'm going to put big brackets here. I'm going to put the antiderivative, which I remember I increased this exponent by 1 and I divide by this. The reason I remember that is because if we want to take a derivative of this, the derivative dx of this thing should give us the same as the original. So derivative of this equals x to the 3 minus 1. Bring down the exponent 3, and we have the original 3 here, which cancels with this one. This gives us x squared. So now I know that this is the correct antiderivative. Anywho, I haven't done a calculus class. I hope you guys are a little bit good with your integration here. But I'm showing you guys here that this is the integral. So we have a 3 here, 0.3, 0.4. Same kind of process as before. The 3 stays on the outside. What we have on the inside is 0.4 cubed over 3 minus 0.3 cubed over 3. This should give us the right answer. So let me go actually to a more complicated calculator so that I don't have to fumble around with the basic calculator here. Okay, I'm gonna plug in everything all at the same time here. So I got 3. Inside I got 2 fractions. The first one is 0.4 to the power of 3. Denominator is 3, all of that being subtracted by another fraction. Numerator has 0.3 to the power of 3. Denominator is also a 3. Let's see if this gives us, this looks like the right answer, 0.037. So now you can put a box around this. This is a probability. So if you multiply this by 100, what you get is 1, 2, we get 3.7%. So the probability of finding the particle in this region here is 3.7%. And I hope you guys were able to learn something interesting from that. Final thing is the expectation value. So in the book, the expectation value of x, right, of x, it could be any variable, is written like this between these little brackets here. What this looks like is an integral from over all space psi star, the variable which you want to find the expectation value for, multiplied by another psi, and then we have a dx here. So like solving this integral here will give you the expectation value. Now psi star psi literally equals to the absolute value of the wave function squared. Why is this psi star here? This is the complex conjugate. It is a way of doing this squaring procedure with complex values. So let's say your wave function is equal to e to the minus I x. You may see this, or maybe you have another one. Let's say I1, I2, e to the I x. In this case, I star would be, you just add a negative sign in front of where you see this I. That is how you determine a complex conjugate. So this one would be e to the I x. Here, since we don't have a negative sign, we add a negative sign, right? Here we added a negative sign, multiply in front of the I. Negative sign times negative sign gives you positive sign. In this case, the complex conjugate of the second wave function would be e to the minus ix. So these guys are complex conjugates of each other. In this class, you don't need to remember it because if you don't have a function with a I here, let's say we just had our wave function, which was square root 3x, the complex conjugate of this guy is just square root 3x. There's no I anywhere in the equation for you to take a complex conjugate. So the wave function here, psi star, is exactly the same as the original wave function. Does that make sense? Anyway, take a look at this. This is how you find the expectation value. This is why I wrote this here. So we're going to use this in our equation to try to determine an answer. Let me actually double check the bounds. I'm going to pull up the book, go to the summary section to see where they show. So yeah, it is over all of the bounds, negative infinity to positive infinity. So we got psi star x psi. By the way, whatever expectation value, maybe I should write that here. Expectation value. Whatever expectation value you want to find, you just take this equation and replace this. So if you want to find expectation value of A, B, H, most of the time you find expectation value of H because this is the total energy of the system. So if you want to find expectation value of the total energy, you put H here. H gets replaced here as well. So this X, you can consider it a placeholder for any variable which you want to find the expectation value for. Anyway, in this case, we have X, which is the expectation value of the position, X is position. Other variables mean other things. We have here integral. Like we said before, this was square root 3 times x, right? This is psi star. Here we have the x, and here we have square root 3x, which is just the regular wave function. Then here we have a dx. It's important to put a dx, otherwise your integral is incomplete. Now let's distribute everything here. Integral, let's see what we're doing here. So we got square root 3 here, square root 3. Both of those are constants, and we can pull them out because everything is being multiplied. Square root 3 times square root 3 is just 3. Then we have x inside x cubed dx. Now, what I'm confused about here is, do we break this apart the same way? So what I'm asking here is, do we break this apart into an integral from this plus an integral here plus an integral here and cap it off like that? Do we do this? The reason I'm asking that is because if we break it up like this, remember in this region here, the original wave function, if I can pull up my original picture, the original wave function in this entire region was 0. Same thing with this wave function. So you can break apart your integral in any way you want. You can go from negative infinity to negative 36, do this integral from negative 36 to negative 37, this integral from negative 37 to infinity. Whatever way you want to break up the integral, as long as you're consistent with the starting and ending points of the associated integrals, you're just breaking up the area and adding it up differently. So I'm curious, like, well, it technically is like this. So we got a 0 here and we got a 0 here. dx. Remember, because we have the wave function here, which comes down here, and we're calculating it from negative infinity to infinity. And this only exists in this region here. So only in this region here do we have this x cubed dx. You see what I did here? So basically, I have this integral here. I have a 3 here, which I pull out, and then I put big brackets around. So the 3 is being multiplied by all of these things. Just pull out the 3. Then I have this integral here, which I have to remember only applies in specific regions. So this region here I said was 0. This region here I said was 0. This is by the definition of the wave function. The only place the wave function exists is this place. So when we take the absolute value squared, the complex conjugate squared, when we do this procedure here, it only applies to the place where the wave function is non-zero. This changes for every problem. Maybe you'll have a wave function that exists everywhere and is non-zero everywhere over the entire x-axis. So what this tells us is it simplifies our integral from 0 to 1, x cubed dx. If we solve this, we get our value for the expectation value. So this integral looks also fairly similar. I'm going to carry this 3 here. This 3 is just a constant. It stays, doesn't do anything. Big bracket like this. Antiderivative of this guy is same thing as before. Add 1 to the exponent, divide by this. If I take a derivative of this 4 comes down. You subtract this 4 by 1, you get x to the power of 3. The 4 in the front cancels with this 4, and you get x to the 3, which is the same thing as what we had in the beginning. A derivative of an antiderivative gives you back the original function. That, I think, is the like an important thing in calculus 1 or 2 or something like that. Anywho, I carry the bounds here 0, 1. So now I can do the same thing I had before. Plug in 1 here, I get 1 to the power of 4 over 4. And then I have minus 0 to the power of 4 over 4. This 0 goes to 0. This 1 over 4 stays 1 over 4. Then we get 3 over 4, which equals 0.75. This is a percentage. Multiply that by 100, you get 75%. Actually, this is not a percentage. This is the expectation value of x, which is 0.75. So if we take a look at the original graph, the expectation value is saying, if I measure the quantum system, it's a probabilistic system. Whenever you measure something, different shit's going to happen. So whenever I measure the system, and if I measure the system like 20 times, 30 times, 40 times, imagine you're flipping a coin. What is the most likely position I would find the particle? Since the wave function looks like this, and the wave function is describing the position of the particle, the expectation value of the position of the particle is 0.75. Meaning most of the time, if I measure, I'm going to find the particle exactly here, 0.75, between 1 and 0, which kind of makes sense because you can see the wave function has a larger, like more area in this region here. So you're more likely to find it there. There's other problems where the wave function looks like this. It is a square well. So where are you going to find the particle here?